Welcome to another exciting biomedical imaging class. In our last exciting biomedical imaging class, we had an assignment where people were using bit operations in order to be able to do interesting and wonderful things. How'd that work for you? Yeah, I got 2 thumbs up from Brian. Rich, good. Kevin?
I got it to encode, but I
couldn't get a decode. So, Kyle? This works? Mike?
I think it went alright.
All right. Okay. I don't see. Oh, Arodi, are you here? You're back there. Yeah, it was okay. Okay. I think Darren had some issues finding the JDK, but now it's there. It was lost, but now it's found, and so his feet will hit the ground finally. So here's the deal. Exclusive OR is one of those things that is used, I don't know, all over the place in unexpected places. Like, for example, when you do graphics, when you draw using exclusive OR, you essentially erase the pixels that were previously drawn. If you're in error correcting codes, when you use the syndrome for correcting the bit error, you exclusive OR the syndrome bit back into the original bit vector, and that resets the original bit vector so you get back to where you were. So in effect, when you use block coding, and we haven't talked about this at all, but it's one of those things, you can always find exclusive ORs are in there. When you're block coding for error correcting codes, it's a whole other topic which we haven't discussed.
Not like Simulink, right?
No, not Simulink. Block coding has to do with matrix multiplications in order to be able to encode and decode bit vectors before you transmit them in a noisy channel. So it's a off tangent, off topic area, but you'll find exclusive ORs are in there. If you want to do I know the technical name is going to throw you for a loop. They call it a random number generator, but in proper parlance, for those who are in the know, it's called a linear congruential generator. And for the linear congruential generator, which sounds like a very fancy name, which we'll abbreviate LCG, for the LCGs, they use exclusive ORs all the time. And essentially all they're doing is exclusive ORing the taps off a shift register and feeding them back with an OR statement in order to be able to shift them in. And this causes a series of random numbers to be created. And those are how the random number generators work in the math.random library for Java. They're the standard mechanism in the field for doing random number generation. And it's all done with exclusive OR. So exclusive OR, it's there for you. It's one of those things, it slices, it dices, it's just magical. And people use it for all kinds of interesting and wonderful things. I also wanted to impress upon you this idea that image processing is really little more than two-dimensional array processing. Two-dimensional array processing is one of those things that we should be able to do and have good facility with. And so one of the things I was working on today was a little toy problem. I love little toy problems because they kind of drive the lesson home in a very simple way. So what I thought I would do is generate a random maze, and if the random maze has a solution, I should be able to plot the solution. So I thought, well, let's do the random maze in an array of character, and then find the solution to this random maze. Now, you know that what happens if you generate a random maze is you may not have a solution. And one of the things that happens when you don't have a solution to the maze is you get a stack overflow because you exhaust yourself trying to search for a solution using a recursive algorithm. So I thought, well, let's just give it a try and see what we can do with it. And so I have this thing called the maze generator, and I then proceed to solve it. So here's the maze, and it's being plotted out with the most elementary of two-dimensional graphics I could conjure. Right? You could do this with a teletype. Right? S means start. Okay. E means end. Okay. Dots are space, and the hash marks, which, by the way, if you're really in the field, are called octothorpes. The octothorpes are used to form the boundary of the maze, and also to form the obstacles, the little walls in the maze. And if you randomly place these things, it's possible to generate a maze that has no solution. In fact, it's quite likely. But here, the I am done is printed, and then we see a solution where we start at S and then we work our way down. Is this the world's most inefficient maze? We're hugging the wall. This is not a good solution. It is a solution. So it's what you call the right-hand wall solution, which means you're walking through the maze with your hand on the right wall, and then you just keep walking until you run into the end, and that's it. Now, it's not the most efficient solution because it's not searching all possible paths, but it will converge to a solution for the maze if one exists, and otherwise throws out like a stack error. So then I thought, well, you know what? That's one representation of the maze, but what would happen if we wanted to convert this lousy image into like a real image for image processing? Well, it is a real image. That's an image. It's an image. One character is a pixel. But if you wanted to use a buffered image from the java.awt package in order to represent it, what would you do? And then I said, oh, that sounds simple. And 8 hours later, I had a solution. So this was one of those things where after having worked on it for a while, I can tell you it's deceptively easy looking and deceptively hard to implement. Deceptively so. How would you turn that into a proper high-resolution image for display on your computer screen? I know the answer. I'll show you the answer, but I'd rather hear you guess the answer first. Any? Yes, sir.
I would map each character to an image that I would to my program and give it access.
Ah, that's very interesting. So essentially what you do is you create an icon, right, or a little perhaps 10 by 10 square, and then you would glue all the squares together.
Or at least display them together. I don't know how I'd get that in one.
You can assemble a bunch of images into one image, but consider how many I guess news you would have to create. So many new 10 by 10 pixel arrays. Then fill each one with a specific icon. You could certainly do that, and then that's a great solution. That'd work. I don't know it's the world's most efficient thing, but it doesn't matter about efficiency if it works. That's an algorithm. It works. Any other ideas? I didn't take that approach, by the way, but that's okay. Any other ideas? How would you do it? What if you wanted to allocate an image all at once? If this is a 20 by 20 character array, and it is, would it make sense to make a 20 by 20 pixel image?
Yeah, I was going to say, do the same kind of mapping, but each character have a different pixel color.
Oh yeah, every character could have a different pixel color. So hashtags could be black, and the dots could be white, and maybe start is green because that means go, and E is red because that means end. Yes?
Start with like a white base and then like XOR to fill in.
Sure. So we will start with a white image. How big should that white image be? I don't think it should be 20 by 20 pixels, do you? Because it's going to look like that on your screen, right? It's got a tiny little thing. What should we do? Make a big image, right? So if it's 20 by 20 here, how about if we make an image that's like, pick a number, 10 times bigger, 200 by 200. So a 200 by 200 image, that sounds good. Make the whole thing white. Sounds good. Then you encounter a hashtag and you want the, border to be black. So how do you know how to color in the image?
XOR. Did you say you could erase that way?
You can erase, sure, but how would you make it sort of green if you want to start? Any ideas? Make a new buffered image. You can do that with ImageUtils. Call imageutils.getBufferedImage and pass in two numbers, 200 by 200, and out pops a buffered image. Bingo. There's your buffered image. Now what? So now I got a doubly nested for loop. I can go through every single one of the characters. That's trivial. Okay, so here comes a hashtag, and we're in location 0, 0, upper left corner. Now what?
Graphics class to draw.
Ooh, a man after my own heart. Yes, if you go to the graphics class, and you can get that off a buffered image, you can call fill rectangle. And if you call fill rectangle, you can fill a rectangle in starting at 0, 0. You can give it a height and a width, 10 by 10 pixels. And how would you set the color on that rectangle?
Use RGB.
Well, oddly enough, in the graphics context, you can call set color, and you can pass in any color you want. Now, it turns out the color class has a bunch of predefined colors. Color.green, color.red, color.blue. Those are the primaries. There's also color.white, color.black, and there's a bunch of others. Bunch of other colors already predefined for you. So that's what I did. That's exactly what I did. I went to the maze solver. I asked it for the image, and so I wrote a little program. Right? A little image to maze, maze to image. Yeah, maze to image. So maze to image. Right? Here's the deal. I get my randomly generated maze string, and I set the maze in my maze utility, and then I get the characters off the maze utility, and then this is the afternoon's labor, right? My amazing get maze image, and then I display it. Then I print it out so I can still have the ASCII thingy going. Then I solve it, and I print it out again so you can see the ASCII solution. And then I call getMazeImage again so you can see the solution drawn on the screen, and display it. And here's how it works. And this is what happens when there's no solution. Why wouldn't there be a solution? It looks like there is a solution. Oh, I think what happened here, I can see there isn't a solution. You can't get in, right? You have to get in this corner. And since the red is blocked off, there is no solution.
So you can't go diagonally.
You can't go diagonally. That's against the rule. I don't know if that's a stupid rule, but there it is. That's a stupid rule. It is a stupid rule, but there. So now that gives you a nice solution. How's that? Yeah. So you start. Here's the start. Here's a thing where you're hugging the wall, and then you eventually get down to the answer. Sweet, right? Now, what's the difference between this solution, which shows something going on in the upper left, and this solution down here, which shows the lower right? Well, somebody got their X and Y backwards, right? But that's okay. That's normal for me. Getting things backwards, I've been doing it all my life. Right? I mean, you can fix that. That's fixable. Right? How would you fix it? Well, when you're getting the maze image, I'll show you how to fix it as I show you the image. First of all, getMazeImage wants to take an array of char, and that's kind of an interesting thing to want to do, and turn it into a buffered image. And what it does is, if you start with a 20 by 20 array of char, you want to end up with a 200 by 200 image, because a 20 by 20 image would suck, and no one could see it. And then what you do here is you just multiply your width and height by 10, and you all should be somewhat familiar with like how to deal with arrays. So I'm not going to belabor that point. And then here's what I'm doing. I'm going through rows and columns, and then when I set the pixel x and y, I'm thinking this is the backwards part. It should probably be y and x, and I'm not sure how I got that so backwards. Maybe if I do this, y, x, right, this is the tedious part. Sorry to make you sit through this part. And then go y, x. And you can see where it says color red, and that's the part where I'm actually assigning the color by calling set pixel. And what I'll do is I'll show you the set pixel implementation. That's my own little subroutine, which is designed to kind of like make life a little bit easier for the programmer. Here's yx, yx, and now you can see x, that's part of the path. So I colored that in blue, so you can see this is the trace that he's trying to give you. S, that's the start, and I colored that in green because start, in green means go. And then E is end, so I colored that in red, so that's the stop, and red means stop. And then the dots, they're all white, and the whole thing is black by default. So I initially set it to black, but I said, look, if you created a new image, all the pixels come out in black by default. They're not set, so I didn't have to do that. So I commented it out. And now I'll show you how you do the set pixel thingy. And set pixel goes to the buffered image, gets the graphics, which is just what Brian said, and then the RGB quantity, which is this java.awt color, comes in, so that gets set, and then I do a fill rectangle, and I say I want it of a specific width and height. Now, I didn't have to do it that way. I didn't have to go and get graphics and set the color. Instead, I could have gone and done a bi.set RGB, right? And I could have done set RGB and wrote a little for loop to build a little rectangle starting at location X and Y and set all the different pixels to an RGB quantity. And then I would have had to have gotten the RGB int from the RGB color, and then I would have had to have set those bits with the bit flipping thing that you guys were taught over the last week when you did your homework. Did I just go too fast on that? No. No. I'm getting a fancy look from Brian. Okay. So we won't do that. So that was my way of dealing with it. Now, did I have to use fill rectangles for this? No. Could have used anything, right? What did they have here? Fill ovals. I could have used fill ovals? Yeah, sure, why not? Fill ovals. And then when you run it, it looks rather peculiar. Oops. Somebody made a mistake. Error. Fill ovals. Sweet, right? Actually looks pretty cool. What? This solution looks weird. No, I mean, look at what he's doing. He's going down here, he goes up in there, he goes down in there, he goes over.
Yeah, because he can't go diagonal.
Because he can't go diagonal, so he's doing.
Goes down first.
Yeah, he had to go. He went over in here, and then he went back. He went up in there. He's still trying to hug the wall, and he went back. This solution is just. It's like, you know what it is? It's like It's like a drunk walk. It's a random. It's like a Markov process almost. It's bizarre. But anyway, it came out with the right orientation. Even if it did come out with ovals, we can set that to anything we like, actually.
So does the program not realize that was a dead end?
I'm not really liking my solution to these mazes. You guys could make a nice solution to the maze. You don't have to, suffer with my lousy solution. It seems like something you should be able to do, right? Can you solve mazes? What were we doing here? Fill rectangle? Fill rectangle. I wonder what fill 3D rectangle does. Okay. Sorry, got distracted. And we're back. Actually, that looks a little bit better. I don't know why fill rectangle looks so much better than fill oval. You know, if you look at the fastest micro mouse contest winner, they're always solving these mazes very efficiently. Have you ever seen the micro mouse? Oh, it's a great oh, you must see it. You've never seen the micro mouse? Never heard of the micro mouse? It's been going on for decades. The micro mouse contest is a small robot that finds its way through a maze, and everybody competes. I mean, really, everybody. It's a worldwide competition. No, everybody but me. But I mean, if you think about it, it's kind of like why is the iRobot Roomba so kind of dumb, right? I mean, it's just like so random in its attempts to clean the house. It doesn't like know anything. It just keeps bumping into stuff. It like cleans by the Braille method. So
There be a way of programming so it knows where your house.
thank you. Yes, if you have any notion of geometry and spatial reasoning, you don't just have to like go in a circle until you bump into something and then hug the wall and then be random about it. You should be able to like do it a little bit more intelligently.
Yeah.
So the micro mouse contest
They gotta pay somebody to program it.
winner, I think there's an image, a video. Yes, of course, there's a video. If you see this guy run, let's see if we can see. Now watch this guy go. Allow full screen. That's how you run a maze. And then he does the inverse maze, and he can go on a diagonal. That's not remote control. No. That is autonomous. Completely autonomous.
Do they know the maze ahead of time?
No, they don't. That's part of it. They can make it, and they go.
Is there another way? How would it never go? How does it look ahead so much?
It first. This is after it explored the maze.
Okay.
So it has a computer. It goes through and it explores the maze, however slowly, and then it has to run the maze solution it thinks is fastest as quickly as it can, and that's how you win the contest.
Okay.
And you can see a whole series of these micro mouse winners. I think this one is in Japan or Korea. I forget. And when the guy is done, he just gives a polite little bow. This is a big deal. These things.
When the mouse goes in the maze, it doesn't just do it one time and then all of a sudden knows the best path, does it?
Yeah, it does just once. It only needs.
It learns the best path.
Yeah.
It has time to explore it.
Well,
Right?
yeah. I mean, is this a Let's see if this is this is a different one, right? No, they use infrared to try and track the wall. So you can see he's exploring now. So this is part of the. He doesn't know the solution to the maze. So considering the fact that the maze has never been seen by this robot before, it has to do exploration and go down blind alleys in order to find the solution. So the exploration process can take time. Well, it's an awfully big maze, isn't it?
Yeah.
Right? And so your question is, how did he go so fast? He's already gone through an exploration phase and then stored the entire maze. Now he should be able to find his way back more easily. Or not. He seems a little confused. Oh, maybe he's finding... Oh, he's looking for a better path. It's not image processing. It's just, well, you might call it an image. He's using his infrared transmitters to be able to detect the presence of a hole in the wall.
So when he's at the end, how does he know that that's the end?
There should be, yeah, there should be a special marker. You see the red marker there? He can detect it when he's gone by it, so he'll know when he's reached his target. These mazes are standardized, and you can buy them, so that you can buy the walls and then configure them however you like. And in this way, people can run their robots in advance of the contest, so that they can be tested properly. Now, one of the chapters in image processing in the book is called morphological signal processing. And in morphological signal processing, what I do is I do a maze solution based on the image. So you take a picture of the maze from on high, and then you edge detect it, and then you find a proper path for your autonomous land vehicle, a safe path, one in the center of the obstacles. And it's not really a maze; it's actually an arbitrary structure. Well, this goes on for 10 minutes. Let's fast forward. Presumably, we don't need to watch the whole thing, right? And then here's the answer, right? He knows the answer. He should be able to... Oh, what he's doing here is he's clearing the dirt off the wheels. He's got something sticky, and he needs the wheels to get good traction in order for him to get a nice speed. A lot of people do that in the beginning for these little robots. Oh, that's a shame. Oh no, he has to go back and he's in shame. It's just do they commit hara-kiri over this thing? It's not. Don't be ashamed. It's a very good attempt. Let's see if he does another one here. All right. I have a feeling this is going to be a winner this time. This thing is just blazing. Yeah. Well, I gotta say, that's impressive. No, these guys are building custom robots, but you can buy pre-assembled robots for this contest. And so Parallax sells a kit which allows you to use a pre-assembled robot, but then you're not going to have a winning robot. You're going to have a very sluggish, slow robot. If what you want is a winning robot, you're going to have to do a lot of custom work. And nothing like what these guys have done is for sale. Although, good Kickstarter project. That's a good one. You get those things out there, people will want it.
So how come it's not very popular here?
Actually, it is. The Micro Mouse contest started in this country. Yeah, and it was an IEEE contest. When I was in high school, they had it, Micro Mouse. Byte Magazine wrote about it in the 70s, and it was all the rage. Here in Connecticut, they were running Micro Mouse. I remember. Now we do FIRST robotics contests, and the robots are quite large, and that's for high schools.
They're all sports related also.
Yeah, they play basketball, things like that, and they're big robots. I beg your pardon? Do they do boxing? I don't know that. There used to be something called Robo Wars that would, you know, yeah. I mean, this is one of those.
On TV. They had the robot wars.
Robo Wars, yes, I think so. So, I have this maze solution, which I don't feel is very good. It's not very good, is it? No. How does one solve a maze? Find the shortest path. So how would you find the shortest path? Try all paths. You can certainly do that. Can you generate all possible paths through a maze? Yes? Okay. And let me ask you a question. How does the number of different paths grow relative to the number of obstacles in the maze? Beg your pardon? Well, if I have a single obstacle, you can go above it, and then you can go below it. So there's two possible paths with one obstacle. Now suppose I add two obstacles. Well, you could go above one and then above the next, or you could go above one and then go below the next, or you could go below one and then above the next. So in effect, you've doubled the number of paths. Now suppose you have three. In fact, I can prove to you that it's an exponential increase in the number of different possible paths, and therefore the maze finding shortest path problem is an NP-complete problem, non-polynomial. And so what that means to me is that since the number of paths grows exponentially, right? In fact, it's like 2 to the n number of paths. If I had three obstacles, there'd be 8 possible paths. And if I had, 16 obstacles, there'd be 65,536 possible paths. Right? I mean, it's growing quickly. Right? So the answer to your question is the number of different paths grows exponentially, and therefore, if you have a large maze that you have to explore physically, that exploration, if you're going to explore all possible paths to get a shortest possible path, is going to be exponentially longer as the maze grows. Has to be, because just mathematically it grows exponentially. So, yes, you can certainly explore all paths and find the shortest path. But the shortest path planning problem, being NP complete, is not a particularly nice problem to have to solve. It's not. Of course, we're solving relatively small problems. 20 by 20 matrices, not large, especially when you consider we have multi-gigahertz machines. We'll solve them like that. So if you want to do an all-path possible solution, I think that's great. It'll probably work real fast.
Well, with the path thing, all you have to do is just out of the paths that actually, were you talking about the ones that actually get you to the goal, or even if you run into a dead end?
Well, you have to look at all paths, and most of them will be longer than the shortest path. Perhaps all of them will be longer than the shortest path, except for the shortest path, unless there's two shortest paths. And what will happen, of course, is that you can use a few different algorithms, I should think. Right? What would be an algorithm to generate all possible paths?
Like in words?
Yeah, I mean, just sort of tell me. How would you program this? Well, I could go and hug the left. Then I could try another one where I hug the right, or I could try right, like Roomba. Right? What does Roomba do? Roomba, I'll try left and then right and then left and then right. This is one of those things. It has to be an allowable, right? An allowable means you can't go through a wall.
Look how big the maze is, and then after that, look how, regardless of how many obstacles, what's the shortest range,
Yeah.
and then see what fits that.
Yeah, I think my solutions are not good, right? I mean, I couldn't win the Micromouse solution contest with this one, could I? I don't think so.
Maybe by luck.
By luck? I have an algorithm for doing maze solutions that doesn't use all possible paths, and it's using a greedy-based heuristic, and it actually does a heuristic search. Some people might even say it's artificial intelligence, but in fact it isn't. It only exhibits intelligent behavior, which is really different than artificial intelligence, according to some. So, as I would say, this sounds like a problem that's reasonably easy for you to do, but isn't. It sounds easy, but it isn't. Yes, sir.
Well, I can think of a couple like hacky ways to do this.
Okay, I like hacky.
Given the fact that you know the shape of the maze, but I was going to ask if your algorithm kind of deals with, say we change the endpoint or something. Did you create the algorithm in a way that can look for all kind of maze shapes?
Yes, I use image processing. See, here the maze solution starts with a character representation of the image, but I started with pixels. A pixel representation of the image to solve the maze. And then I used a start point and an end point, and then I did morphological image processing and skeletonization. And that's what's described in the book chapter, I think it's chapter 12, on morphological image processing. So starting with an image and solving the maze is actually quite a bit harder than starting with the characters and solving the maze. So I would encourage you to start with the characters, but if you prefer, you could start with the image. I mean, here's the image, and it's a clear start and a clear end. And if you started with an image and you wanted to solve the maze with that, you'd have a whole lot more cells to explore, because you now have a 200 by 200 maze instead of a 20 by 20 maze. And we've just shown that the two are essentially equivalent. So why not start with the 20 by 20? I think, me personally. So how would you explore this maze to get a let's start with the maze over here. How would you explore this maze? How would you generate the paths, all possible paths?
I wouldn't.
You wouldn't.
No, it's 2 to the n. That's ridiculous.
Well, I mean, 2 to the n. If 2 to the n is like I don't know how many points there are. How many different possible paths are there here, anyways? A lot, right? A lot. A lot. How about this? How about if we use a greedy algorithm? Greedy algorithm says if you go this way and the distance to the endpoint doesn't decrease as much as if you go this way, then you go that way. So the greedy algorithm, which is kind of like what they call hill climbing or local optimization, says going this way gets me. You want to come up with a metric of goodness, and to me the metric of goodness is your distance to the goal. So if what you do is you try and find a path that gives you, two alternatives, and one gets you closer to the goal than the other, you take the one that gets you closer to the goal.
Is that a good?
It'll give you local optimizations?
But what if you have obstacles
Okay, so let's
And then it can have to back up.
let's run the mental exercise. So now I go down and I'm getting closer, and then I go down and I'm getting closer, and I keep going down, 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 down. But then you say, aha, what happens when I reach here? Right? I ran into an obstacle, so now you've got to backtrack. Right? And so then you go this way, and that gets you closer to the goal, and then eventually you go down. So when you go down and then you hit something, you need an algorithm that's going to allow for backtracking. I say wall hugging helps, which is kind of what I ended up doing. So when you look at it like that, essentially this looks like a backtrack right in there, and then it comes back up and then goes down, trying to get to the E, but then it hits it, and then it goes back up, and then goes down, and hits another bump, and then goes back up, and comes down, and goes back up, and then comes down. In some sense, it's going through the tracing that you would probably have to do in order to find the solution. It's showing the trace. I would suggest that just some of the side excursions could have been missed. Right? So I'm not sure. I mean, maybe there's a nicer algorithm. What if you use, there are these paths. You could use a flood fill algorithm. A flood fill algorithm says what we'll do is we'll explore all possible paths by going this way and that way, and keeping track of each one as we go, and just filling up the area by going to all adjacent places. You've seen flood fill algorithms work before. In paint programs, you take a bucket and you click on some area, and the entire area becomes colored in with the same color. There's some paint program in Windows that does that, has a bucket. So a flood fill algorithm might be a way to go. How else could you do this? You could Google it. You guys use Google to find stuff, right? I'm sure you don't just make up stuff on your own. Yes?
I was thinking of, so you're going to go left to right at any given point.
Well, I'm using a simple algorithm, right?
Yeah.
But you guys could do anything you want. I don't care.
Well, my idea was that if you're going to go left or right to get to your destination, well, excuse me. If you're looking down, you're going down or right? Because the destination is down to the right.
Well, it doesn't have to be. You could set the destination anywheres. In fact, if you think about it, you know what the shortest path is between 2 points? Straight line.
Yeah.
A straight line.
Yeah.
So why not just do that? Why not draw a line between S and E, and then see if you can't move in a straight line toward S, and then if you bump into something, go down, and then just keep going toward S in a straight line. Keep going. I guess you have to go this way and then that way, and eventually what would happen? You run into this, and then you have to go that way, and you run into that, and then you have to go this way. But if you're using a straight line, then essentially you'll eventually get down to E in smallest time. So if you have the line between x1 and y1 and x2, y2, and you want to generate all points between those lines, how do you do that? How do you create the parametric relationship that generates all the points between two lines? Right? Let's do that. I mean, that's not too hard, right? Let's assume S is in location 0, 0, and E is in location, let's call it 2020. And let's call the x1, y1, and x2, y2. How would I generate the integer points on the line that exist between those two locations? How would you do that? Right? You guys know how to do that? A for loop. Well, sure, a for loop, but I mean,
1, 1, 2, 2, right?
yeah, I mean, let's assume for the moment that you want a simple line generator. I guess I'll put it in the maze program. I don't know. new Java class. I'll call it line generator. Okay. So here's the line generator. And what we'll do is we'll say something like this. If you have a point, we can give it a location. So we'll say point P1, Alt Enter. Let's try the Java AWT point, because that uses integers. And we'll set it equal to new point, and give it a location. I think we said 0, 0, right? And then there was another point, point P2, and we'll set that equal to a new point, and we'll make that pick up a number, 19, 19. Okay. And now I want to create the points that range between point P1 and P2, where P1 and P2 can be arbitrary locations. So now I'll generate the locus of points that start with P1 and end with P2, and I'll use a dummy variable which ranges from 0 to 1 in order to do it. So someone said use a for loop, and that's exactly what I'm doing. For I'm going to use a for loop with a double precision number. Double t equals 0 while t is less than 1. T equals t plus 0.1 n paren. So now I have a dilation parameter t which ranges from 0 to 1. And I would like to generate the locus of points between P1 and P2. So what I'll do is I'll create a point which will be a new point that is in between those 2 points that gets closer and closer to P2 as t gets closer and closer to 1. So it'll start at P1 and end up at P2. So what do? Well, P of t is going to be equal to, when t is equal to 0, we want all P1. Right? So it'll be P1 times 1 minus t. So when t is equal to 0, it'll be all P1. And when t is equal to 1, it'll be all P2. So we'll say t times P2. Right? So now it's clear. As t ranges from 0 to 1, at 0 we'll have all P1, and at 1 we'll have no P1 and all P2. You could do this with color. You could do this with geometry in an arbitrary dimension. P1 and P2 could be 3D, could be 4D, could be how many Ds you like. D, 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 D. So in a sense, this is a generic way to represent a parametric locus of different points which are traversed as t ranges from 0 to 1. Is this sort of making any sense? I mean, there are 2 ways you can represent geometry. Okay? One is the implicit representation, which I'm demonstrating here, and the other is the implicit representation, right? Which is, if you think about it, a line is y equals mx plus b. That's an implicit representation of a line. But the parametric representation of a line segment, which I'm using here, is just as legitimate and far more useful. If you think about it, the same thing happens with a circle, right? X squared plus y squared equals r squared, the implicit representation of a circle. But the parametric representation of the circle says I use sine of t and cosine of t. And that's much better, right? Because then as t ranges from 0 to 2 pi, I form the locus of points that go around the circle, and I get a whole bunch of different points. So whether or not I want to use a parametric or implicit representation is open. It's an open question, depending upon the application. But for the case of generating a locus of points, it's much better to use a parametric representation of a circle. Why? Why? Why can't I do something like this? X squared, well, I guess I can. This is x squared plus y squared equals r squared. Right? You know why? Because that's not a function. That's a relation. Right? Function has exactly one value for any value of x. But here, because you have plus or minus when you go and take the square root, in order to solve for y as a function of x, you have two different possible values, the top half of the circle and the bottom half of the circle. Well, that's very good if what you want to do is get an analytic closed form solution for the intersection of a line and a circle, but it's very bad if what you want to do is draw a circle. So what you really want here is not the implicit representation of the circle. You want the parametric representation of the circle. You want the representation of the circle that says x is equal to the cosine of theta, and y, or maybe r times the cosine of theta, and y is equal to the sine of theta. You see? Now, as theta ranges from 0 to 2 pi, I'm putting in the r's so you can have the equivalent representation. So now as theta ranges from 0 to 2 pi, you will have exactly the locus of points that goes around the circle. And you could say, but the two are equivalent. And I'd say, okay, yes, that's true. But from a computer graphics point of view, they're not equivalent at all. Because now what I have is a mechanism by which I can generate the circle from the equations. You see? So a parametric representation is quite powerful and important for us. And then comes the question, how do you generate that sucker? I could probably do that with a static method, right? That's not a bad way to go. So maybe I say something like this: public static point, and then get point on a line, and then I put in a point P1, and then I put in another point P2, and then I put in the dilation parameter, which is a double, that's T, and now I'm going to implement this little guy right in here. And so I make a new point, and now I can say P1.x times 1 minus t, just like it says in the comment, plus t times P1 dot y, t times P1 dot y, and did I write P1 when I should have written P2? P2 dot x, sorry, P2 dot x, and why is that wrong? Oh, I need a comma.
Why is it P1 dot x?
Nope, I still did something wrong. Just a minute. I want the x part and then I want the y part. Maybe I'll do this in 2 steps because I'm making a mistake. Integer, let's see, we'll call it x equals, there is a plus sign in there. That's why I'm screwing it up. Pardon me for skipping. What could possibly be wrong here? Oh, I have to cast it to type int. Because floating point contagion. Floating point contagion says when you take a float and multiply it by an int, you get a float. So if you really want an int when you're done, you got to go cast it back. So now, ask your question again, please.
Why is it P1 dot x?
Okay, so P1 and P2 are two-dimensional points. And so P1.x is the x component, and P1.y is the y component.
Is that like a method of the point class?
Yeah, the point class is really nothing more than a data structure that holds x and y components, like an imaginary number. So now I got the x part, I got to do the same exact thing, only I got to do it for y. So effectively I can just copy and paste this and change the x into a y to give me my new points. And now, at the end of the day, and this is terribly inefficient code, but I don't care because it's for education, I'll just say return new point of x comma y. And that point is a point which lies between P1 and P2 and is going to move rather smoothly toward P2 as t ranges from 0 to 1. And we can show that to be true. We can do the following. We can print out the points. S out, Control J, Enter. Get point of, and then it says P1, P1, comma P2, comma T. And that should dilate smoothly as we go from 0 to 1 with T in order to be able to show us points that range from P1 to P2. And sure enough, you can set P1 and P2 to any two points in the Cartesian coordinate integer plane, and this is going to create a series of coordinates which will approach those points linearly. So this is the trajectory you would like to track, right? Because someone said something like, "Oh, Professor Lyon, the shortest distance between 2 points is a straight line." Somebody said that. Someone. And so if that's the case, then maybe we should try and find a way to get the robot to track those points. That's very greedy. That's a greedy method, right? Nice heuristic method. And the further away we are from the straight line between the 2 points, the more distance will have to be traversed through this maze. And these are all integer points, so we can determine whether or not there's an obstacle in the way as we move from one point to another. But isn't there a problem with moving directly from point 0, 0 to point 1, 1? Yes, because you can't move on a diagonal. So you need the Manhattan distance between the 2 points. The Manhattan distance says that it's as though you're moving along the streets, and you have to go from streets to avenues in order to be able to do your maneuvering. And you can see the micro mouse was kind of busy doing that. It really wasn't constrained to only move left and then right. It was able to move along diagonals. But in this case, it does seem like there's some, I'll call it impedance mismatch. But at least we can do arbitrary points, right? I can make the point anywhere as I like. I can make it 12, 13. And presumably, this will still run. I see a little duplication there because of the round off, but that's all right. It eventually gets to the end. You know what? I think you could probably make this a little bit coarser. Make it a 3 or something like that. There you go. The number of increments between the two endpoints should probably be a function of the overall geometric distance between the 2 points, right? So if you know how many cells there are between 1212 and 1919 by doing a simple metric like x1 minus x2 squared plus y1 minus y2 squared, and then take the square root, then you should be able to compute exactly what the increment should be on t. I'm thinking. But that's kind of a refinement. All I wanted to do was find a solution to a maze. Someone said this sounds easy. Didn't someone say that? No, nobody said that. Nobody said that.
Check the tape.
Huh?
Let's check the tape.
Check the tape? Rewind the tape? I think I thought it looked easy, but it really wasn't, I think is what I said. Something like that. Not that easy. But you guys can do this, right?
I think handling obstacles seems difficult.
Well, I mean, it's just a two-dimensional array. You'll get your feet wet with the arrays. Anyway, I thought it was a fun one. Don't you think that's fun? Doesn't it seem fun? Yes, very fun. I'm not getting the yes, Professor Lyon, it's fun look. Sorry. I'm sorry it's not fun. This sort of thing should be fun. We did some of this stuff last time, if not most. Oh, this is the annoying... I have a distinct, unpleasant recollection.
Turn the volume down.
Turn the volume down. How does one do that? You know how to do that?
Yes.
There should be like a button, right? Oh, I thought it was a function key. I'm looking
I'm
for
sure
a shortcut.
It is, but this is the easiest way.
That's not going to kill the audio for the people who are listening, is it?
It shouldn't.
Okay.
Speaker volume.
Right. Speaker volume. All right. So this is where we were at last time, and we were doing. I think we got through all of this, didn't we? This is the sampling thing. We talked about what sampling is. We talked about Nyquist. You guys know Nyquist's theorem? Humor me. Tell me Nyquist's theorem again. Rich, help us.
I always remember half, but I can't remember the rest.
Yeah.
Half. Half. Half.
Sampling rate
Sampling rate. Something about sampling.
has to be double the highest frequency.
Ah, thank you. You've been brainwashed. I mean educated. Yes. It turns out you have to sample at twice the highest frequency you intend to reconstruct with the Nyquist theorem, and that's in theory, not in practice. In practice, you want to sample a little faster than that, and then you need a roll-off filter in order to be able to prevent distortion so that your signal is suppressed by the time you get to the peak sample rate. So as it turns out, if you want to measure something like these bars in here, you've got to have a pixel resolution that's just twice as dense as the density of the bars. And then we got into bitwise operations, and then you guys did an encoding and a decoding, which I thought was very fun. We did the arrays, and then we talked about row major versus column major, and that's when I thought, geez, wouldn't it be fun to do a thing with mazes? And that's why we started to get amazed by the mazes. Now, the business about changing row major to column major, that's one of those basic sort of code refactoring things that you can do. It's equivalent, but it gives you different sort of runtime behavior. I'm getting quizzical looks from Kyle.
I'm like quizzical.
The difference between row major and column major, you saw me do that when I swapped X and Y, right?
Yeah.
Because everything got rotated around once I did that. The question then becomes, what would leave us with the maximum memory coherence? And then, of course, the answer was, we don't know, because the Java language specification won't tell us. So the only way we can tell is by benchmarking, but the benchmarking is going to give us an answer which is Java Virtual Machine specific and will not be portable. So now we can't write portable image processing code if we use an assumption about whether we're in row major or column major. Doesn't that stink? Yes, Professor Lyon, that stinks. So it's a big question, right? Because if I go this way, left to right, top to bottom, then what happens is I get numbers that look like they are coming off in row major. But if I go this way, bottom to top, left to right, then I get what's called column major. And you can see the numbers that you're generating are really very different. All right? Really very different. So then, how do you figure it? Well, this is one way to deal with it. Take y and multiply it by the width, and then add the offset x. And that will give you a way to simulate two-dimensional arrays. A way to simulate two-dimensional arrays. So, how does that work in terms of, the actual coordinate which you're getting? Like, if you look at this, let's see if we can look at it. Can you copy these things? Ah! What's it doing? Stop! Stop! I want to copy. Okay. Copy. Thank you. This is a very non-cooperative program. So let's play the pathological adversary and show what happens when you do it wrong. So here is the prototypical example of memory incoherence. Let's be incoherent. Incoherent memory. Incoherent memory. Let's see how that works when we have incoherent memory. So what we'll do is we will generate a index which would be used to input into, I'll make this static even though it's really bad form, static width equals, let's say, 10. And we'll make that an integer. And then we'll make this static over in here. Everything will be static, because I don't care. Public static void main, Control J, Enter. So what I'd like to do is I'd like to write a doubly nested for loop. For integer I equals 0, well, let's use x. X equals 0 while x is less than with x plus plus. Let's pretend width and height are the same. For integer y equals 0, while y is less than width, y plus plus. And now what we'll do is we'll print out the value for the index into the one-dimensional array when we try to get a pixel using x comma y. Alright? So let's do that. And so now look at the numbers as they get created. We're jumping all over the place. Alright? This is bad. We're not accessing sequential memory. That's clear, right? So as I go from x from 0, 0 to 0, 1 to 0, 2 to 0, 3, it's like I'm jumping the whole width in memory. That incoherent memory access means, from a computer architecture point of view, there's going to be a cache miss on every single pixel access. That's going to hurt me big time because I won't be able to do a prefetch on an entire block of memory. Now let's take the exact same code with a difference, and we'll go y comma x. Right? So now we're going to do column major first. And now when we run, ta-da, we have memory coherence. We're accessing the same exact pixels, but we're going linearly in memory, which means we can do a prefetch. We have good memory coherence. It's a big win. We can fill our superscalar pipelines. We can execute multiple instructions in a single clock cycle. We're going to generate what I would call orders of magnitude faster code. Really faster by like a lot. So this matters, right? Having X and Y being executed properly in the proper order makes a big difference. Big difference. Now, if you said to me, well, I like X to be first and I like Y to be second, I could say, yeah, me too. Right? But if you want it to be this way, well, what are you going to do? Well, maybe you could change the way in which this for loop accesses X and Y. So if you do Y in here, and then you do X down here, you interchange the for loop. So what does that buy you? Ta-da!
So it's rows first.
Great. So now you're going in row major order, and you're assuming that is how the pixels are stored when you index them for your processing. So if you're doing that sort of thing, X is for you go Y first, and then X second, and then that's row major. And that's key. That's so important. So this is a row major way to store your data. This is the row major way. Got that? Row major versus column major. So important.
It doesn't matter which one you use, though, because we don't know.
Well, if you're going to store pixels that get accessed by Y times width plus X, then you are definitely row major, if that's how you store your pixels. So if you store your pixels in a one-dimensional array, and a lot of people do, then you can access them in a row major fashion if you use this Y times width plus X mechanism. And I always assume row major. I always do left to right, top to bottom. And it's been reasonably fast in the Java virtual machines that I've encountered. So that's kind of why I write the code that I do. But you know what? Because of the Java language specification, unless you store everything in a one-dimensional array and start to do stuff like this, there's really no way to control how these things are going to be accessed. A couple of things you can do, however. I've got these different loop transforms. And the loop transforms that you do, these are coding transforms that I've used in the past that essentially allow you to do things that are optimization hacks. I cannot say enough bad things about them other than they can make your code a lot faster. And the optimization hacks essentially allow you to take bundles of the arrays and process them so that they fit exactly into the CPU's cache. So these kinds of optimization hacks are little more than bit flipping, right? There's really minute understanding of the computer architecture that will enable you to make highly optimized code. Should I take a break? Is it break time? Let's do that. Take a 5-minute break.